Find a vector orthogonal to the plane through the points P, Q, and R. And B, find the area of triangle PQR. So how do you find a vector orthogonal to the plane through those points? Yeah.
Well, I defined the plane by finding the vector PQ and the vector QR.
Got it. Stop. Good. So you went and found, what is it, 5? 5 and 1. So now what you have there is you have two vectors that start at the same point. So if you cross them, what do you end up with? Yeah, so if we crossed PR crossed PQ, is that going to face up or down based on that diagram that I just drew? Upish or downish?
Up.
Upish, that's right.
So
Upish.
PR2P2.
Yeah, so it's going to go
Boardish.
like this. There you go. Like that. Good. So we actually cross them. And you're going to do this a bunch of times. So 1, 1, 1. And again, which should I do? 4, 3, -2. Does it matter which row I write? It does. So let's see which one this comes up with. So what's this going to be? So we're interested in 1 times the determinant of 3, -2, 5, 1, minus 1 times what?
4, -2,
Plus 1, 4, 3, 5. And these are actually, we're kind of breaking these up into, these are separate components, right?
What is that symbol?
I was just breaking it apart, a line. So it's going to be 1 times 3 minus -10 I. And then what's the ij? So it's going to be negative what? 1 times 4 minus what? -10 again. J, comma, 1 times
20.
minus 15. Okay, so what do you end up with? You end up with 13i
-14j.
and how many people agree with that answer right there?
From what we just did.
From what you did. How many people agree with it compared to the work that you did? It's exact vector. Can someone give me another answer that you got? If you didn't get this exact one, what did you get for this question? If you didn't get this answer right here, can you tell me what answer you did get? No. What answer did you get? You did the homework. What answer did you get if you didn't get this one? Okay, we're going to pause this here because you're obviously parallelogram. So if you want the area of the triangle, what do? It's 1/2 of that. Could you handle doing that on your own? Yeah. You know how to find the area of parallelograms with cross products. All polygons can be broken up into a finite number of triangles. In this case, 2 identical triangles, so you just divide by 2. Okay, moving on. The same initial point. You can draw this parallelepiped. You see this right here? Okay, so here's the deal. Here are the 3 points. Sorry, the 3 points have the same initial points, so the 3 points are right here, here, and here. If those 3 points are in the same plane, what is the volume of the parallelepiped that they form?
Nothing.
0. It is 0. If they're coplanar, there's no height to it, right? In the area formula that it says in your book, it gives you, I think, this A dot what? B cross C. We can come up with a reason for that in a second. So, does it really matter which one you choose as A, which one you choose? Well, actually, get A, B, and C, right? Great. So what are you going to do here? Let's do B cross C first. We have, what is B? 1, comma, -1, comma, 0. And what's C? 7, 3, 2. So how are we going to cross these two things? Well, it's the same 3-dimensional matrix. 1, -1, 0, 7, 3, and 2. So what are you going to get? You're going to get 1 times -2 minus 0 I, right? And then -1 times 2 minus 0, j. And then 1 times what? 3 minus -7, k. There's your vector for the cross product. So what does that come out to be? 2, +2? No, -2, right? And 10. So now you're dotting that with a. What's a? 2, 3, 1. So then you're doing 2, 3, 1 dot -2, -2, 10. And that's a dot, and this was b cross c right here. So what do you end up with? -4 plus -6 plus 10 is equal to? So the area is the magnitude of that, which is absolute, which is 0. So therefore, these 3 points have to be. Yes, Josh.
The book had a
Of the position and the force vectors, and measures the tendency of the body to rotate about the origin. The direction of torque indicates the axis of rotation. So the vectors you really want to pay attention to here are, here's F right here. That could be where you're pulling when you're turning something. And then here is R, the actual handle, the thing you are turning. So if you cross these two things, which vector is perpendicular to both of those vectors? Tau. Tau is right there. So if you literally took F, you can think of F as if you joined F and R at the origin, it's easier to see the perpendicular relationship there. So does everybody see what I'm talking about in terms of where the 90-degree angles are? You have a 90-degree angle right there, and then if F was right here, you'd also have a 90-degree angle there.
So theta is 90 degrees.
In this case, this angle is 90 degrees. That is correct. No, this angle is definitely not, doesn't have to be 90 degrees. No. If you get a more efficient turn if you go this way, or do you want theta to, optimally, what's the optimum angle for theta? 90. The most force would be transferred to turning this nut. Exactly. So all you really need to remember is torque is going to be the cross of the vector for the R and the vector for the force. That's all you really need to remember. That's it. If you remember that, then you can easily get it. Most of your work on these problems is going to be figuring out what those vectors are and being careful about units, which I am bad with. That's right. 0.18, that's correct. What about F? 60. And then we need sine of
80.
80, exactly. The angle between the arm. Exactly. So then could you use your calculator to get an answer to this? Jay, what do you get?
10.636.
10 point what?
636.
Okay. There it is. This is just another thing to remember. This is not bad. We're good with this? Okay, so let's talk about lines. So, can someone tell me, or can you see what the connection is? So this is the parametric form right here, and this is the symmetric form. How do you get from here to here? What's missing in this? What's missing in those? T's gone. So what do you do to each of these equations right here? What do you solve for? You solve for t, and then you set them all. And what do you end up with? The symmetric. So are all of these ways of writing a line all very, 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 very closely related? Yes. Sometimes it's going to be helpful to have the symmetric equation. Sometimes it'll be helpful to have the parametric equation. And sometimes it'll be helpful to have the vector equation. So there are 3 forms that we're going to be working with for lines. 3 forms. We have the vector equation. We have the, I didn't write it down there, I clipped it off. Parametric. And we have the symmetric right there. Those 3. I would say parametric is probably going to be the form you're going to be most frequently dealing with. Okay, I got to dig up a problem now. Our vector equation is of the form r naught plus t times v. V is parallel to the line. So r naught, how many different r naughts did we decide we could have on a given line? Which one do you want to use?
A.
A or B, right? We're given A and B. There's no reason not to use A or B, right? Could you make these arbitrarily weird? Sure. Let's use A. So we're going to say R naught is 2, 4, -3. So T, you don't solve for T. T is just the index variable. So what do we need to solve for? What's the only thing left? V. V is parallel to the line. So how do we get the direction vector? How do we get the direction vector? Go from A to B. Go from A to B. So what is V going to be? You can actually do this out. V is going to be the vector 3 minus,
2,
comma, -1 minus,
4,
comma, 1 minus, yeah, 1 plus 3, exactly. So V in this case is going to be 1 and 4. That is the direction you're heading in. So what do you end up with for your, what? Yeah, look, find the vector, parametric, and symmetric equation for the line that passes through those points. Does that description give you a direction? No, so we're just picking one of them. We're just picking one of them. So are there multiple answers to this question? Yeah, you have lots of different R naught values. It could be either direction. I'm just going from A to B because it's alphabetical order for no other good reason. So this is our direction. So our vector equation, we're going to end up with 2, 4, -3 plus T times 1, -5, and 4. There's our vector equation. Every point that is on that line is described by some T value. How many points could we then generate for this line? How many points could we generate if we wanted to? As many as we wanted, right, by picking T values. What? T's a scalar. It's the index, just like any, it's the same T from any parametric equation you've ever done before. We good so far? So this is the vector equation. Once you have the vector equation, you're pretty much home free. Can someone tell me just off the top of their head what the parametric equation is going to be? Yeah, so let's go back and see what one looks like. We have that right there. X is x naught plus TA, right? So x is going to be equal to 2 plus t. What's y equal to? Yeah, and z is equal to plus 4t. Yeah, there's the parametric definition. Exactly, right. So if you solve, so that's the parametric. So if you wanted the, what's the last one called? Do you remember? Symmetric. That's fine. That's certainly close enough. That's fine. So in this one, you end up with t is equal to x minus 2. T is equal to y minus 4 over all over 5, -5. Thank you. And t is equal to z plus 3 all over 4. So in this case, the symmetric equation is going to be x minus 2, and it's proper to say over 1 equals y minus 4 over equals z plus 3 over 4. You'll notice something here. See the denominators there? 1, -5, and 4. What is that? This, yeah, you both. That's great. I love it when the harmony works. Usually the cacophony fails into this chaotic mess where people say the answer is 7, 18, 45. No, v and the direction. It's the same thing, right? Yeah. Look what you have here. There is the direction vector. So there are ways to go faster between these that you will learn, but for now, once you get the vector equation, can you easily, or should you be able to easily determine the parametric and the symmetric versions? Yes, absolutely. It's going to be a segment from A to B, and T goes from 1 to 0. So when T is 0, it's at A. When T is 1, it's at B. What do we have to let's just take a look at what we had up here. Let's go back up here. What did we have? We had this right here. Let's clip this out. We had this thing right here. Let's see if ours actually does that. Well, when T is 0, so if it's R of 0, what do you end up with? 2, 4, -3, which is A. That's good, right? Great, yay.
We won.
Because we chose A as our initial point. Yeah. Let's try R of 1. What's R of 1?
3, -1.
3,
And one, oh, wow.
-1, and what?
1.
And 1. So what is that?
B.
In this case, this is exactly what we want. If we went from A to B, T is 0. It starts at A, T is 1. It goes, oh yeah, it should work out that way because how did we get our direction vector? We found the vector from A to B. Does our direction vector have to be that exact magnitude?
No.
No, the only thing we care about is the specific direction, exactly. So could we turn that into a unit vector?
Yeah.
Yeah, is it really common to have direction vectors be unit vectors?
Probably.
Yeah, unit vectors pop up all over the place. So let's say we change this. Let's change this just a little bit. Let's change it to, if we went from B to A. What's our new initial point?
3, -1, 1.
3, -1, and 1, plus, plus T times, now we have to be really careful here, right? What do we have to do?
The opposite.
The opposite of the direction vector, so it's going to be
-1, 5, -4.
-1, 5, thank you, and
-4.
exactly. So that is the one that goes from B to A and exactly lines up perfectly. Does this can be a little more complicated? Hold on. I want to put this one thing up there. So you understand what we're trying to build at this point. This is what I want to put up there. Another way to write it, and it's much more common. This is the story time. If a given line passes through the tip of R and R1, so if you have two vectors like this, so R0 and then another point on the line, then the direction of the line is R1 minus R0. So the vector equation of the line, you'll notice something here. What did I do? You'll see this 1 minus t here. Does anybody know where that comes from? So, ready? Let me draw this. I'll pause it. Constructing the line is not super hard. You just have to polish it a little bit if you want it to be a segment that starts at a certain place and ends at a certain place. You just have to be careful. If the question is asking you to start end in a certain place, you have to be you have to limit what your answer. You have to just be careful. I'll say it that way. If it doesn't matter if it goes on forever, it's a line. Are you a lot more free to do what you want? Yeah.
Pick a direction vector of 520.
Yeah, exactly. Yeah, exactly. Hold on, what? -1, exactly. What's the direction vector here?
2.
Sorry, no, it's 0. No, it's 0. You're right, 0. No. It's 2. It's 2. The initial is 2, 1, and 4. So you have a direction vector for each of those, right? Can you arbitrarily pick a starting point?
Yeah.
So this is the direction right here. How would you go about finding any starting point? Pick a value for t or s. What's a good value for t?
1.
Or 0.
Oh.
Plug in 0. So what would be an initial point here for L1? 1,
-2.
4. So you have an initial point and a direction. Can you write the equation of a line?
Yeah.
And then can you try to intersect them by doing some algebra?
Yeah.
And then can you fail miserably at it?
Yeah.
And then you can conclude
They don't intersect.
they don't intersect. Also, are these scalar multiples of each other?
No.
Ah, other thing. Okay.